So, hey there, before we start the quick challenge, assume that the same task is given to the two DevOps teams. Nevertheless, as you can see, the first team still working hard, while the second seems to be ready and partying hard. That makes the question, what makes the difference between the two cases?
Java and Erlang?
No. So, but these guys definitely use Metalon, that is an operation and maintenance tool for Erlang, and also my love child. So, I'm Viktória Fördős, the leader of the Wombat project, and today I share our latest experiences with you. The experiences are related to Wombat and gained in the context of the EU-founded release project. The aim of the release project is to introduce radically new software development technologies that can exploit multiple heterogeneous clusters consisting of multi-core machines in a reliable, scalable way. In the context of the release project, the main task of Wombat is to provide the scalable infrastructure for deploying thousands of Erlang nodes. In this talk, I will tell you Wombat's secret. That is, how Wombat is able to scale out to thousands of nodes to detect anomalies, prevent incidents, understand your system, and be your best friend. Okay, it sounds good, but well, what kind of incidents and anomalies? Actually, I brought to you some illustrative examples to highlight how Wombat can help you in real life. Well, half a year ago, we were on site at the customer, helping them in polishing their new product just before going on live. Well, Wombat was in hand and pointed out some real problems. Here you can see the first problem. Actually, some Erlang nodes belonging to the same Erlang cluster use different versions of the MongoDB application. Consider how big would have been the surprise if this had turned out on live. And actually, considering that detecting the root cause is not straightforward, well, thank you, Wombat. Actually, Wombat told this problem to us as an alarm. Well, another example I'd like to show you is another alarm. It says that the ETS count exceeds the limit of the ETS tables on an Erlang node. Actually, when it happens, the VM crashes. In advance, Wombat raises an alarm that is definitely your last chance to prevent the outage. Cool. So I guess everybody is curious about Wombat's secret. Then let me tell as a story. So the story begins when we were preparing for the final evaluation of Wombat in the context of the release project. There was one question. What is Wombat limit in practice? Or to rephrase, how does Wombat behave under massive load for a longer period of time? Is it reliable? Well, actually, soak testing can answer all of the questions. Soak testing is a testing technique that helps you to determine whether the system can sustain continuous expected load. Well, this is exactly what we were looking for. So, we designed and developed the soak test and also a development process that helped us to utilize the outcome of each execution and to improve Wombat. So let's see first the development process. So the development process was consist of crazy sprints. At first, we started the soak test and we left it alone at least for a week. Of course, we checked periodically whether it has already crashed. Yeah. And then we analyzed the results to find errors, anomalies, and early bad signs. We browsed the log files of the system and collected the errors. Next, we analyzed the collected metric data by studying the graphs. We were looking for signs of overload. You know, when you can see large message queues. And we were looking for serialization problems. It is very likely to occur when a few running processes are in the system and hundreds of waiting processes are still there. And we also paid special attention to spikes and repetitive patterns. We checked the raised alarms, and we also paid attention to was the alarm cleared? If so, the system was able to recover automatically. Then it's okay. Otherwise, we need to improve it. And next, we compared the result with the previous runs to decide whether we improved the system or not. Yeah. After we collected the problems, we examined that. So actually, for each error, we tried to detect the root cause. And then we were thinking about how Wombat could get in such a state. Was it a timing issue? Maybe a serialization problem? Overuse of transactions, global locks? Maybe we were sent too much messages, or yeah. And then we quickly addressed as many issues as possible. Actually, fancy PRs weren't made, as the improvements need to be validated by the next soak test at first. You know, all the glitters on my guard. And next, we set up a new soak test. Once the system became stable, we increased the load and let it crash again, again, and again. So, and how we soak tested Wombat? Obviously, the subject of the soak test is Wombat. But as Wombat is a monitoring tool, of course, it monitors some Erlang nodes. And actually, the Erlang nodes should do something that exercises Wombat well. So we employed Basho bench that commanded the Erlang nodes how to behave. With this approach, these Erlang nodes became the nightmare of Wombat, actually. If Basho bench commanded the nodes, became extremely crazy. So for instance, thousands of processes were being spawned within each node. And each process sent a huge number of messages to each other. And then they crashed because of various reasons. You know, Wombat monitors the node by injecting agents into the Erlang nodes. So in such a bad Erlang node, these agents still needs to function and provide the input to Wombat. Yeah, but it is only one point of view. Actually, consider the user's perspective. The responsiveness of Wombat must be maintained even if it is being flooded by a huge amount of input from the managed nodes. So we employed Metalon to simulate users. That is a load testing tool developed by Erlang Solutions. Yeah, Metalon queried data from Wombat. So Metalon was the one who simulated the data retrievals. And actually, it seems to be ready, but not, because we had an extra Wombat for observation purposes. It recorded everything what happened in the soak test, and we used its data to improve Wombat. So how could Wombat help us to improve Wombat? Well, so here you can see the total memory and the process memory that are related to the soak tested Wombat collected by the monitoring Wombat. Here you can observe the repetitive pattern as it's like to be a little bit dangerous. Actually, we investigated this problem and found out that the root cause was one of our scheduled activity. Yeah, here what we did is that we decreased its memory usage and improve this schedule. Actually, the activity is now performed less frequently to prevent possible outage. Consider that the outage could happen when two scheduled activities overlap with each other. Okay, here comes another example. This page displays alarms in the system. Usually an alarm is your last chance, so ignoring alarms can easily result in critical situations. Actually, don't take the chance, react. So here we can see two alarms. The first highlights that the CPU load is extremely high, while the second tells us that there are more than 10,500 messages in the mailbox of a process. Large message queues are harmful as they consume a huge amount of memory. So actually, we investigated and found the root case. That was a process. Actually, a process crashed, then recovered, performed many operations, and sent a huge amount of messages, and finally crashed again, and in an infinite loop, of course. Yeah, so we fixed this bug. And here you can see a more extreme case of large message queues. Actually, such message queues predicts that the internal throughput of the subsystems are greatly different. In this case, the weaker subsystem can be easily overloaded, so you need to find the balance. Okay, now you can see a very, very short video that presents a great feature of Wombat, that is the live matrix. Live matrix can give you an insight what's happening on your system at the moment. Here we can see the CPU utilization of the soak tested Wombat, and what I did here is to switch on and off the metric that is related to one of the core of the machine on which the Wombat was running. Okay, now you can see still the Wombat's GUI, where we are querying some exometer and Folsom metrics. And now we are querying the gauges of one of the managed nodes. Yeah. Now we are going for the log files, and we request to present all the logs that is related to one of the managed nodes. We can visualize the detail of a log file, of a log entry, and then we can go for the alarms. Here you can see that I filter the alarms that is related to one managed node, and then I extended the scope of the presentation. Okay. Oh, and what I need to note that the last video was about the soak-tested Wombat. So actually, the soak-tested Wombat was under a very, very massive load, but nevertheless, it was very, very responsive, as you can see, you could see. Okay, but so the outcome of the soak testing was a big win. Actually, we stabilized the tool, we improved its performance, reliability, and responsiveness. We increased its capacity. That is how many nodes can be monitored by one Wombat. But unfortunately, we were still very far from our goals. One Wombat can manage between 150 and 200 nodes reliably, but our goal was to manage 10,000 of nodes. So actually, further analysis was essential. So, but here what we learned, that we really, really need to analyze our system to know its limit. Okay. So we went for further analysis, and we found out that the root cause was the Wombat's old architecture. It was actually the initial prototype. And when the guys were designing the initial prototype, actually they dedicated themselves to two tasks. The first task was to create the first proof of concept, and the second task was to ensure great scalability to manage thousands of nodes. Okay, let's see. So the old architecture was a layered architecture consisting of 3 layers. The top was the REST layer. That is the main interface to communicate with Wombat. And then there comes the master layer that provides topology services, and it acts as a router between the REST and the middle managers. Oh, and the bottom layer are the middle managers. They were communicating directly with Wombat agents. You know, they are running on the managed node. Actually, multiple middle managers can exist, and they can be deployed to a set of Erlang nodes. It seems to support the scalability, or not? But there is always a but. So because of some consistency reasons, the architecture was too centralized. All requests went through all the layers, including the master layer, that managed the centralized data store. So the problems were, requests were serialized, the centralized data store was a single point of failure, and also a bottleneck. So we concluded in that we had to think about Wombat's architecture again. We dedicated ourselves to the following goals. We should not introduce again bottlenecks, single point of failure, and an overly centralized architecture. So actually, lessons learned, however, it was quite expensive. Nevertheless, good advice, do not over-architect your system in advance. So, okay, let's do it. Re-architect Wombat. So here comes the key observation. Grab your popcorn. So actually, one Wombat can manage 200 nodes. Then 6 Wombats can manage 1,200 nodes. Okay, but they are separated from each other. What to do? Well, let's build a Wombat tree. Why not? So actually, this is the new architecture of Wombat, where the old Wombats are the building blocks of the new system. The managed nodes are the leaves and are the children of a worker Wombat. And as I said, worker Wombats are the old Wombats, so we avoided the complete re-implementation of the tool. And these worker Wombats are the children of the root node. The root of the Wombat tree is the so-called meta-Wombat. Okay, so let's roughly examine the overall system at first. Observe that worker Wombats are not aware of each other. They exist in their separated worlds. So, in the world of a worker Wombat, there exists a meta-Wombat and its managed nodes. This world restricts and defines the responsibility of a worker Wombat at the same time. As not all the nodes are visible to a worker Wombat, it is only responsible for the nodes it knows about. Well, by limiting the world of a Wombat, we also limited the information. Well, at first sight, it sounds as a problem, but actually, it is a benefit because by this, we control the maximum amount of information with which one worker Wombat can deal. And now, it is very, very unlikely to overload one worker Wombat. Okay, but as you can also observe, meta-Wombat is not directly linked to nodes, to manage nodes. Yeah, this is first great. Meta-Wombat cannot be overloaded. But what happens to the managed nodes of a dying worker Wombat? They shouldn't be left alone without supervision. So, meta-Wombat knows the necessary information about all managed nodes. I mean, the host, the node name, and the cookie. So, in case of a worker Wombat died, it reassigns its managed node to another worker Wombat. Cool. And what about MetaWombat? So, as I said, it is the main entry point of the system. It is also the coordinator of the system. As the Wombat tree is transparent from the users, users only interact with MetaWombat. So MetaWombat can be considered as a big router between the users and the worker wombats. It routes the requests and the responses between the users and the worker wombats. It is, as I said, the coordinator of the system, and it's also responsible for managing the Wombat tree. Actually, it only starts new worker wombats when the actual capacity of the system is not enough to fulfill a new request. And it also distributes the task among the worker wombats. So I mean, what kind of task can be given to MetaWombat? It can be, please monitor for me an extra node. Please deploy 10,000 Erlang nodes. Okay, cool. So these are the tasks. And these tasks are distributed among the worker wombats. And as I said, it also supervises and manages the worker wombats. So it is aware of the free capacity of a worker wombat. It is aware of the information about the managed nodes monitored by worker wombats. And well, MetaWombat also stops worker wombats when there is no need for that. But when can it happen? Actually, when all the managed nodes of a worker wombat was removed, so when there is no need for a worker wombat, MetaWombat stops it. Yeah. And MetaWombat is actually a purely parallel approach that is the cooperation of concurrent processes. Okay, and how Erlang nodes can be deployed using the improved system. Okay, here you can see a simplified flowchart, and I promise I won't add here on details. So, user sends a request via REST interface. Of course, it arrives to MetaWombat. MetaWombat checks whether the capacity of the system is enough to fulfill the request. The free capacity of the system is the maximum number of nodes can be assigned to a worker wombat without overloading the system. If the capacity is enough, then MetaWombat do nothing. Otherwise, it starts new worker wombats to be able to fulfill the request. Then, it distributes the tasks among the worker wombats and initializes the deployment. After that, it requests the worker wombats to deploy the subset of the Erlang nodes that are their responsibility. Cool. And then MetaWombat waits for all the worker wombats to finish their task. And then MetaWombat orchestrates the newly created Erlang cluster. After that, of course, it informs the user what's happened and what is the result of the request. Okay, so with the improved system, all of our goals were reached. This is a distributed application, even in terms of persistence. The approach makes worker wombats independent from each other, thus they do not affect the scalability of the others. The reliability of the system is confirmed by soak testing. Thanks to the built-in recovery mechanisms added to MetaWombat, it can recover itself and the whole Wombat tree after any failure. Cool. So, we evaluated Wombat on Ethos cluster in the course of the release project. Actually, here we were, we were able to use more than 200 multi-core machines to deploy instances of the end colony optimization release. Well, at first, we were interested in the time required to deploy end colony, to build the Wombat tree, and then to deploy the nodes. So, well, here you can see the deployment time that is based on our experiences. And here, the main observation is that the required time can be expressed linearly with the size of the input. For instance, hundreds of nodes can be deployed in 2 seconds. Let's see a concrete example. So we deployed 10,000 nodes within 210 seconds using 67 worker wombats to 139 machines. And besides this, we observed another interesting thing that is related to the construction of the wombat tree. Actually, that requires 10 seconds regardless of the number of used worker wombats. So MetaWombat is purely parallel approach. Okay. And the second thing that we were interested is the effect of the monitoring. Actually, the overhead of any feature not contributing to the result of the execution needs to be very, very minimal. So we wanted to make sure that the generated overload of wombat is small enough. So we measured how much time does a certain computational task takes when wombat is only used to deploy, and measured when wombat overhead is minimal, and measured when wombat also used to monitor the nodes. The difference of the two is the overhead. Well, we found out that wombat overhead is minimal for a few schedulers, but it is very serious if the number of schedulers exceed 16. Actually, wombat was not behaving nicely. It was very similar to the wombat in the video, so it actually not allowed the manage node to do its actual duty. The manage node must play it with the wombat. Yeah. So we investigated this problem, because actually it was a problem, and we found that the root cause was calling Erlang system monitor to monitor long GC. Actually, it sends messages for us when garbage collections takes too much time. Well, yeah. Then we went to the VM's code, and we found that this statistic uses Erlang now. Actually, what you need to know about Erlang now is that it puts a global lock on the whole VM. It means all the schedulers are blocked. So our solution was that we extended it monitoring long GC with a condition. That is, if the machine is really multi-core, we disabled monitoring long GC. With this improvement, the overhead vanished. So we measured then the execution time of the end colony optimization algorithm with and without monitoring. The difference between the measured values is the overhead of the monitoring. The blue star depicts execution time when the monitoring was turned off, while the red rhombi depicts execution time when the monitoring was turned on. So the maximum overhead was less than 1.5%, so we consider wombat that it is non-intrusive. Okay, here you can see a very, very short video how we performed experiences on the Ethos cluster. Actually, it tells you, it presents the deployment of 5,000 echo nodes followed by running the algorithm itself. So we, oh, my fault. But I have some time. So we sent a REST request to Wombat, and then it is performing the request. Now you can hear that the echo nodes are coming up and up and up. Then we are waiting for all the nodes. And after all the nodes are up, MetaWombat starts orchestrating. Actually, in this case, it means that it set up the master at the echo algorithm, starts then all the echo releases in each node, and then waits to terminate and collect the results. Cool. So, in conclusion, the evaluation process established the following characteristic of Wombat. The effect of the monitoring on the managed nodes is very, very minimal. So Wombat is non-intrusive. Wombat has the ability to dynamically scale out in size, and it has the ability to deploy thousands of Erlang nodes with linear deployment time. So, to concluding the conclusion, I can say that distribution is your friend. Good. So actually, besides this, Wombat has many other attractive features. It can help you to deploy and manage thousands of Erlang nodes, even in heterogeneous superclusters, even in the cloud. Wombat can even help you if your system usually a regular load is put it on your system, but sometimes this load increases very, very greatly. In this case, Wombat can notice that your cluster is being overloaded. It rents extra machines and distributes the load on these machines. After that, Wombat can notice that the cluster is underutilized, so it removes some machines from the cluster and release the machines back to the provider. So it helps you to minimize your maintenance cost, actually. Wombat can help you to prevent outages using alarms. Actually, our alarms are customizable, and we have more than 25 built-in alarms. We also have some special alarms for React and Nasia. And another good thing that these alarms can be directly connected to PagerDuty. Yeah. And as Wombat, the aim of Wombat is to provide an Erlang-specific view of your system, and it's do not want to compete with existing tool. Of course, we support the integration of Wombat to another third-party tools. For this reason, we provide ready-to-use applications that can channel the data collected by Wombat to these tools. And, well, we also automatically collect Exometer and Folsom metrics and Logger or SESL log entries. This all aids you to understand your system better, to provide the visibility of your system, and to help you in detecting its weakest part and improving your system. So, today I told you a story about Wombat, and I shared lessons learned. I emphasized the importance of the soak testing. Actually, I presented an approach that I think can be easily tailored to any system and can help you to know your system's limit. It is very, very important. Actually, the soak test is running at the moment still. So we really like soak testing. I also presented a counterexample about over-architecting systems. So be agile in mind, focus only on one big task at once. Address issues if they occur, and not in advance. And finally, I presented you the new architecture of Wombat. It is parallel, distributed, reliable, and scalable. It is able to deploy 10,000s of Erlang nodes. Wombat is non-intrusive. The effect of monitoring is very, very minimal. And we created this new architecture by avoiding the complete re-implementation and we use the old system as the building block of the new system. And actually, I ask you to remember that developing massively concurrent large-scale softwares requires distribution, really. But actually, all of us are very, very lucky as Erlang provides built-in support for distribution. And last, I like to spread the message of Wombat. Wombat says he would love to help DevOps who wish to focus on real challenges rather than repetitive tasks, who like to understand and improve their system and sleep tight during the night rather than firefighting. So yeah, thank you very much. Any questions? Yeah.
I'm wondering, so what if that master, I think we call it meta, what if that were failed?
Okay. This is a very, very good question. So the question is about what happens when meta wombat fails, I guess. Okay. Or either wombat itself. Okay. So actually, when meta wombat crashes, we haven't seen it, but of course it can happen. So when meta wombat crashes, it is first restarted by the herd mechanism. That is the Erlang solution to restart systems that are terminated unexpectedly. Next, meta wombat and both wombats are used persistent databases. These are distributed databases, but use them to store the actions being performed and to store the planned actions. Thus, if an execution is interrupted, when meta wombat recovers, it can continue from exactly the point where it was. And also, when meta wombat recovers, it actually checks the health of the wombat tree. It tries to connect to all of its worker wombat. And if some of the worker wombats has died or something went wrong, then meta wombat is aware of the information that is related to the managed nodes belonging to the died worker wombat and can reassign the orphan managed node to a new worker wombat. So meta wombat actually not only construct the wombat tree, but maintain the wombat tree. Thank you. Yes?
If meta wombat dies,
yeah?
do worker wombats continue working and collecting information?
Thank you very much. So the question was, if meta wombat dies, worker wombats can continue, yeah. And the answer is yes. Meta wombat and worker wombats are loosely connected. And when meta wombat crashes, actually worker wombats are still operates. Nothing happened. They do their duty. Their duty is to monitor the managed nodes. Nothing else.
They're not even aware of it.
Yeah.
If
Yeah.
the wombat node crashes, what happens there?
Wombat node?
Yeah.
Which one?
The wombat node, the lower level. The wombat nodes monitoring the managed nodes.
If a worker wombat crashes, yeah. So what happens when a worker wombat crashes? Actually, when a worker wombat crashes, meta wombat is aware of it immediately. And at first, it starts to restart its worker wombat. But it can happen that it cannot be completed. For instance, maybe there is a net split between meta wombat and worker wombats, or who knows? And in this case, it starts a new worker wombat in another node. Yes, please?
Do you use standard Erlang distribution protocol, or you roll something on your own for communication between wombats?
So the question is whether Erlang distribution protocol is used for the communication between the wombats. And my answer is very simple. Yes, it is used. It is cool. We do not like to reinvent the wheels. We use what is cool. Thank you.
You can easily add a secure layer if necessary. No one's requested so far. All of the installations are all behind firewalls for secure environment. The day you need SSL in between the nodes, that can be done, but then you need the managed nodes need to include an application. So you need to include your third-party code, which you don't at the moment. So yeah, you could have had a RabbitMQ cluster running for a few years and then just connect it to it and start monitoring it.
So I was asking from the efficiency perspective and problems with the protocol itself, not from security perspective.
Yeah.
And another question is,
Yeah.
what happens with the data when the worker wombats die? The grab data.
Okay, it is a good question. Actually, when we are able to restart worker wombats, then nothing happens. When the data is very, very critical to the business, then using another built-in Erlang mechanism that is employ takeover and failover nodes, this is how the problem solved in this case. So, and in the most business critical parts, we can of course use real clusters with multi-data centers. Yeah. Any other question? Yes, please.
For the soak time period, you said that you used like a week, I guess, in
Yeah.
terms of the iteration time. Looking back, do you feel that you could have learned all of your lessons using a shorter time, or do you wish that you had used even longer periods for the soak?
Okay. So the question is, well, it is a long question. So usually we use 1 week for soak testing, or we use a longer period of time, or why we use at least 1 week. Is it okay? Cool. So actually, there are many problems that can only turn out when the system is used for a longer period of time. I mean, with empty databases, many applications can work. But if the database is very, very full, then yeah, then can come, then the timeouts can come, and the internal communication becomes much slower, and so on. And of course, so at the beginning of the soak testing, each run was, I think, less than a week. But now, actually, we are able to, we cannot overload Wombat, actually. The soak tests are terminated because we are running out of this space. So, yeah.
It's a good problem to have.
I think so. Thank you. And any other good question? Yes, please.
A little bit about the use cases where you'd be spinning up 6,000 or 10,000 Erlang nodes. I assume you're not talking about full mesh configuration, but that kind of covers.
Yeah. So, for what kind of application?
Are they totally independent Erlang nodes, or what's the connectivity behind it?
I see. Okay. So we usually set up Erlang clusters where the nodes are connected to each other. In the context of the release project, we deployed end colony optimization algorithms. These algorithms are distributed and parallel algorithms. This is something about the ants, the small ants. They are trying to collaboratively solve one problem. And so the communication between the nodes are very heavy.
But a given Erlang node, number 6,000 doesn't know about all 5,999 others.
I'm sorry.
So for a moment, there's a point to point. So yeah,
Right, the full mesh normally.
yeah. So how the clusters you're monitoring is meshed or not meshed. There's a Wombats as there's a hidden node, so it will just monitor
Right, but I was wondering what use cases you would actually see where that would be a practical number of Erlang VMs.
So ad serving, for example, there are a lot of companies serving ads which have thousands of ad nodes in production. They're serving billions of ads per day, real-time bidding.
Yes,
And
and
another company,
typically those-
they've got thousands of nodes.
And those are full mesh clusters?
No, they're not full mesh clusters. Yeah. And so Wombat doesn't really care if they're full mesh.
No,
clusters.
I understand what I was just wondering
Yeah.
where you.
Yeah.
Ah.
So yeah, you've got. I'm just a bit hesitant on what we're allowed to talk about and not talk about, but yeah, there are
Because I
lots.
know there's SD Erlang work.
Yeah. So it doesn't really matter how the systems are done. You know, it's basically
Right.
how they're meshed among each other. What makes it easy if they are meshed is the whole Alpha discovery mechanism. When you connect to one node, it will go in and
Right.
walk its way through and discover all the potential nodes.
Okay, that's one of the problems. I think.
Yeah.
Thanks.
So there's scarily large clusters out there.
Okay, thank you. Any other? No? Then thank you very much.